The question that I have is, could you solve a truss problem by the method of joins? This is the problem that I have selected here. We have a simple truss supported at point A by a pin and point C by a roller. The dimensions are shown in the picture and the truss is subjected to external forces at point D as shown. A 50-pound force in the horizontal direction and a 100-pound force in the vertically downward direction. The question is to determine the member forces and the support reactions. The first step would be to determine if there are any zero force members. If you recall, we covered this in another video. There are two situations in which we could run into zero force members. In that video, we call them case 1 and case 2, and these are the two cases. In case 1, if there is a joint with two collinear members and a non-collinear member with no external force at that joint, then the force on the non-collinear member is 0. In this example, joint D is one of those joints and therefore the force on member BD is 0. BD is a zero force member. In case 2, if there is a joint with two non-collinear members and no external force, then the two non-collinear members are zero force members. In this example, joint E is one of those joints and therefore the member DE and member BE are zero force members. And in examining our problem, we see that joint B fits the description of case 1. In other words, joint B is like joint D here. Therefore, this non-collinear member BD is a zero force member. Our second step here is to select a joint to start the analysis with. Now remember the guidelines. We need to select a joint that has at most two unknowns, right? Not more than two. Because we can only write down a total of two equilibrium equations per joint, right? Now that we have established that member BD is a zero force member, for analysis purposes, BD does not exist. And therefore there are only two members at joint D, and therefore joint D is a good starting joint. What about the other three joints, A, B, and C? At this point, at joint A, we not only have these two members, but also a support, right? Since this is a pin, there are two support reactions at that joint. At this stage, we have four unknowns at this joint and therefore we won't be able to start from it right away. However, if we can first find the support reactions, then of course the number of unknowns is reduced to 2 and therefore we can start from that joint. We have a similar situation at joint C. We have a support reaction. There's only one, of course, which is the vertical force reaction at point C because it's just a roller, right? So if we can find that support reaction first, then joint C is a joint that we could start from. What about joint B? We cannot start from joint B at this stage, although it looks like we could because there are only two members at that joint, right? But unfortunately, both members are in the horizontal direction, and only meaningful equilibrium equation we can write down for the joint is a horizontal force equilibrium equation, and that equation is going to have both of those unknowns and therefore we won't be able to solve for those unknowns at this point. So we have two distinct options here. We either start from joint D, and then in that case we don't have to find any support reaction, or we can start from joint A, but we need to first find the support reactions at point A. Starting from joint C is very similar to starting from point A. So we'll just consider these two and do it both ways. So let's follow route 1 first, that is start from joint D. Then our next step would be to draw a free body diagram for joint D, and here it is. These are the external forces and these are the forces on the members. I'm going to mark them as tensile forces at this point. And here are the labels that I chose for these forces. I call this as FAD and I call this as FCD. Now we need to define the directions for these forces. We could either calculate this angle and use that, or we could use ratios in order to define the directions. Now referring back to this main picture, we see that line AD has a ratio of 4 vertical to 3 horizontal, right? Line CD has a similar ratio, 4 vertical to 3 horizontal. So let's go ahead and use ratios here. So 3 horizontal to 4 vertical mean the hypotenuse will be 5, and same here. Here are my two force equilibrium equations. This is the equation in the horizontal direction, and this is the equation in the vertical direction. Well, let's go at least one of them here. So in the horizontal direction, we have 50 pounds, right, going in the positive x direction, and the horizontal component of FAD is going to be in the negative x direction. The magnitude is going to be FAD times 3 over 5, right? That's what I have over here. And FCD has a positive x component, and the magnitude is FCD multiplied by 3 over 5 again, right? I'm sure you can easily follow the equation in the y direction. So we have a situation where we have two unknowns, two equations, but both unknowns are in both equations. There are multiple ways to solve this equation, so this is what I have done here. First, I'm taking equation 1 and multiplying through by this factor here, 5 over 3. And when I do, this is 3 over 5, right? And you multiply that by 5 over 3, they will cancel out to give you 1. And the same thing is going to happen over here, right? I'm going to bring this 50 to the right side and multiply that by 5 over 3. So this equation simply becomes minus FD plus FCD equals 83.33. Similarly, if I take equation number 2 and multiply through by this factor, 5 over 4, I end up with this equation. Now you can probably see why I did that. If I were to add the two equations, equation number 4 and 5, you can see FCD will cancel out, right? So I'll have a equation in terms of just FAD. And similarly, if I were to subtract one equation from the other, FAD will drop out of the equation. So here are the values I got by doing that. Now we move to one of the neighbors. We have three options, points A, B, or C, right? We are not ready to go to joint A yet, because even though this force is now known, we still have three unknowns at that joint, which are the member force on member AB and the two reactions, right? We don't want to go to joint B either, for the same reason we discussed before. So only option we have at this point is to go to joint C. So here is a free body diagram for joint C. We go ahead and mark the known quantities at that joint. We know the member force on member CD. And remember, we got a negative number, and therefore it's a compressive force. So let's mark it as a compressive force. The force on the member CB or BC is an unknown at this point. So let's mark it as a tensile force, and we still have a support reaction C sub Y at that point, right? So there are two unknowns, FBC and CY, and we can write down two equilibrium equations, and we should be able to solve for these two unknowns, right? So let's go ahead and do that. Here are the details, easy to follow. I'll let you follow. Our next logical choice would be joint B, and here are the details. We get a value for the force on the member AB. FAB equals 62.5 pounds. Now we are ready to consider joint A. The member forces have all been found, but by considering the equilibrium of joint A, now we can find the support reaction AX and AY. Here are the details. Here's a summary of the results we got. For the member forces, you want to indicate whether they are compressions or tensions. Remember, we've been consistent in marking all of the unknown member forces as tensions, right? So if we got positive numbers, they are indeed tension. But if you got negative numbers, they are actually compressions. Now let's repeat the analysis by following route 2. In this route, we're going to start with the joint A, but we need to first find the support reactions. We do that by considering the equilibrium of the whole truss. I went ahead and marked the support reaction. We have a pin at point A, and therefore there are two force reactions at that point. We have a roller at point C, and therefore there is a vertical force at point C, right? Here are the details. I used the force equilibrium equation in the horizontal direction in order to get a value for AX, and we get a value of minus 50 pounds for that. Then I took a moment about point C, and that gives me a value for AY, and this is the value that I'm getting, 16.67 pounds. Then I summed up the forces in the vertical direction, and that allowed me to find a value for CY. CY is 83.33 pounds. Now we are ready to analyze the joints one by one, starting with joint A. Here is the free body diagram for joint A, and here are the details. Two equilibrium equations, one in the vertical direction, one in the horizontal direction. The one in the vertical direction allowed me to find FAD, and this is the value we got. And one in the horizontal direction allows me to find FAB, and I got 62.5 pounds for that. Now we could either go to joint B or joint D, but let's go to joint B. Here is the free body diagram. All we need is just one equilibrium equation, the one in the horizontal direction, and that gives me a value of 62.5 pounds for FBC. Now I consider joint C, and the vertical equilibrium equation gives me a value of minus 104.16 pounds for FCD. We could have also gotten a value for FCD by considering the horizontal equilibrium equation like shown here. At this point, we have found the forces in all of the members, right? So let's go ahead and use the equilibrium of joint D as a check on our calculations. Here is the free body diagram of joint D, and here are the two equations, one in the horizontal direction, one in the vertical direction, right? We find that the forces sum up to 0 both in the horizontal and vertical directions. This kind of checks out our calculations. So did we get the same results as we got by following route 1? Yes, we got exactly the same numbers. So the points to be made here are that there are multiple ways to do problems like this by the method of joints, and there are ways to check our calculations too.